Okay, so for today, I'll be going over three sort of handy exponent rules that you'll be able to use to help solve and simplify your physics equations. The first rule here that we're looking at is about multiplying exponents when they have the same base. So if you have some number, base a to the power m, and you're multiplying it by base a to the power n, then your final answer here will be base a to the power of m plus n. Okay, so this is a pretty simple rule, but it's incredibly useful. The first way we'll be using this is to combine terms, right? So when you're combining terms, you're going to use this kind of operation many times. So let's just have an example here. Let's say we have 4/3 pi r squared, and we are going to multiply this by another power of r. Okay, so what's the answer? Well, if we follow this rule, we see this is going to be 4/3 pi r power of 2 plus 1, right? Because this is actually r to the 1, okay? So when we look at it this way, it very clearly becomes 4/3 pi r cubed. There we go. What's that, the volume of a sphere or something? Okay, so we can have these different powers of r and combine them together when they're being multiplied using this rule here. Very, very common, okay? Now, let's look at another example where this happens a lot. This is going to happen quite a lot when you're using scientific notation, okay? Super common when dealing with very big and also very small numbers, okay? So let's look at an example here. Let's say you are going outside late one night and you look up into the sky and it is a beautiful night sky filled with stars. So you get out your telescope and you're looking and you see in the sky a cloud of gas, a nebula in space far away made of hydrogen gas, okay? And maybe you look up this nebula and you discover that it has a mass of 2 billion kilograms, okay? Somebody figured that out. Now, you're thinking to yourself, you wonder, wow, 2 billion kilograms, that's a lot. I wonder how many atoms of hydrogen are inside that cloud. Well, we can do this. We can do this problem. It's actually not too hard. So first we'll start out with 2 billion kilograms, okay? So that's going to be, in scientific notation, 2 times 10 to the 9 kilograms of hydrogen gas here, right? Now we want to know how many atoms there are in this. So if we know our chemistry, we know Avogadro's number, we know that there's going to be 6 times 10 to the 23 hydrogen atoms per gram, okay? But this is in kilograms, this is in grams, so we're going to need a conversion factor here. So let's do that real fast. Let's move this. And just erase this real quick. Okay, so what's the conversion factor to convert kilograms into grams? Well, we can multiply by 1,000 grams per kilogram, right? That's the conversion factor right here. But it's better if we keep this in scientific notation. So let's say this is 10 to the 3 grams per kilogram. Okay, so now we've got it set up here, and we see that the kilograms are going to cancel, the grams are going to cancel, and we'll be left with a number of hydrogen atoms, which is exactly what we're looking for. Okay, so how do we do this math problem now? Well, we see this is going to be, we can collect all of the powers of 10 together, and we'll have this 2 and 6. So let's say it's equal to 2 times 6 times 10 to the 9, right? This one here, times 10 to the 3, collecting this one here, and then we have this one here, so that times 10 to the 23 atoms, okay? We can do this math. This is going to equal 12 times 10 to the, now we're going to just follow this rule, right? So we're going to add up all of these exponents. It's going to be 10 to the 9 plus 3 plus 23, just like that. And we can then just do this sum. That's going to be 12 times 10 to the, what is this? 23 plus 3 is 26 plus 9 is going to be 35. 35 atoms, okay? And if we want to keep this in scientific notation, then we'll want to move this decimal point over there, right? So we can rewrite this as 1.2 times 10 to the 36. And that's our answer. We have 1.2 times 10 to the 36 hydrogen atoms inside this beautiful nebula that you saw at night through your telescope. And this is a very, very common way for us to use scientific notation and use this sort of exponent, this power rule right here, to add the exponents together and get an answer very, very quickly. All right, let's look at our next rule using exponents. And that's when you have a fraction with some exponent, a base to a power of m in the denominator. And it turns out that this is equal to the same base raised to the negative of that exponent. Okay, and this seems okay, you know, mildly useful. You can see how they're equivalent, but actually the reason why this is so nice is because it's a secret way for us to eliminate ugly fractions, right? So what we can do here is we can use this rule to secretly get rid of fractions. You see, we can rewrite this weird, ugly fraction into something like this that is not a fraction. For example, 1/2. Well, that's a fraction, but we could also write this as 2 to the power of -1, right? No more fraction. Another way of doing this is to look at, say, what's the unit for velocity? Well, that's meters per second. Instead of writing meters per second, you could write meters times second to the -1, right? Because this is second to the first power, right? This is 2 to the first power. And so we can use this rule to sort of kill the fraction and rewrite it in a different way. Let's look at some examples here. Just like before, we can use this rule when combining terms, right? So just like we were combining terms here, we can also use this rule to combine terms. Let's put a quick example here. We'll use the same kind of numbers we had before. So 4/3 pi r squared, but this time it's all divided by r, okay? Let's rewrite this. We can rewrite this as 4/3 pi r squared times r to the -1, right? And now that we've rewritten it this way, we can use our first rule and add these two together. So it's going to be this form here, where it's going to equal 4/3 pi r to the power of 2 minus 1, which is 4/3 pi r. Okay, and there we have it. We've simplified this initial expression into this, which looks a lot better. We've been able to get rid of that ugly fraction and have a more simplified version of it. Another way that this comes really in handy a lot is when you're doing some kind of dimensional analysis. Sometimes also known as unit conversion. And this happens a lot in physics because we have lots of different kinds of units, right? Earlier we were looking, kilograms into hydrogen atoms. We can have something more complicated. For example, let's say we have power. Okay, now power is measured in units called watts, right? What if we wanted to break down watts and write it in its more fundamental components, right? So we know that the equation for power is work over time, right? Now the units for work over time is going to be joules over seconds, right? That's what we have here. But what is work? Well, work is equal to force times distance, right? So the units of work or energy is joules, and that's equal to the units of force, which is newtons, times distance, meters, right? So this is another way of writing down a joule. It's a newton times meter. But what is force? Well, if we remember Newton's laws, we're going to know that force is equal to mass times acceleration, right? So that means we have newtons are equal to kilograms times meters per second squared. Okay, so here we have all of these different unit conversions that we can try and put together. So if the challenge now is to write down watts in more fundamental units like this, how can we get there? Well, we can sort of work backwards. We'll start with a newton, which is a kilogram times meter per second squared, right? So that's a newton. And we know that a newton times a meter gives us a joule. So we're going to multiply by a meter. And so now we have joules. And from this equation, we know that joules over seconds gives us watts. So we divide this by seconds and we have watts, right? So this is correct. A watt is this thing right here. But this is an ugly fraction. Very ugly. I don't like this. Nobody's going to like this. If you write this down as your answer, technically you're right, but it's really ugly. So, can we do this in a better way? And of course we can. We're going to try and take advantage of our exponent operations here. So instead of writing it like this, let's start out again by writing down newtons, but we will write it down a little bit differently. We'll say kilograms, good, times meters. But instead of per second squared, we're going to rewrite this, because it's in the denominator, as second to the minus 2. So we get rid of that fraction right away. No more fractions. Fractions are ugly. Now this is a newton. Now we're going to multiply by a meter to get joules. And then now we're going to divide by seconds to get watts, but we don't want to have a fraction. So instead of dividing by a second, we're going to multiply by seconds to the minus 1. And now we can sort of combine things here, and we see this is going to be kilograms, meters times meters, that's meters squared. Seconds to the minus 2 times second to the minus 1, that's second to the minus 3. And there we have it. This is equivalent to this. These are the same, but look at this one. It is beautiful. No more ugly fractions. Okay, so this is a very useful way of using this rule that's going to come up a lot in physics equations. And now, for our final operation here, our little shortcut, we're going to be looking at radicals. Okay, now radicals are also kind of ugly and confusing, and I don't like them that much, but they exist, so we have to deal with them. So let's say you have a radical for a, but we're taking the, say, mth root of a. Okay, how can we rewrite this? Turns out this is going to be equal to a to the power of 1 over m. Okay, so we can get rid of the radical by rewriting it as an exponent. Okay, so this is what tells us that fractional exponents are actually a way to represent radicals. Okay, let's look at an example here. So let's say we have r squared times the square root of r. Okay, now square root, remember, means there's a little 2 in here. So we can rewrite this as r squared times r to the power of 1/2, right? Because remember, it's like there's a little 2 over here. So we just follow this rule, that's r to the 1/2, and we can combine these together using our first rule, right? This one right here, m plus n. Well, in this case, it's going to be r to the power of 2 plus 1/2. And if we work around with fractions, we could rewrite this as r to the power of 5/2, right? That works. So this is a way of rewriting this expression, and there's no more square root, there's no more radical sign, because it can get a little bit confusing or ugly with lots of radical signs floating around. And let's try one final example to illustrate this again. This time, what if we have r squared divided by the square root of r? Okay, now we've got a double ugly, right? You've got a fraction and you've got a radical. Let's try and simplify this. This will become r squared over r to the 1/2, right? Just using our new rule right here to get rid of the radical. But we can also get rid of the fraction using our second rule right here, right? We can get rid of that fraction. So let's do that. And this is going to become r squared times r to the power of minus 1/2, right? And then we use our first rule to combine these together. This will be r to the power of 2 minus 1/2, which is the same as r to the power of 3/2. So this and this are equivalent, but at least for me, this second one here, that looks a lot more simple. That looks a lot more beautiful. This first thing over here, this term, it's kind of ugly. So there we go. 3 quick and easy sort of exponent shortcuts that you can use to rewrite equations to make them more simplified and sort of easier to understand. Make sure to visit my website. The link is in the description for a PDF cheat sheet with all of these rules on it, as well as copies of the slides. You can also just go to learning.withgideon.com and you'll find everything right over there.